This time we're going to take a look at the area bound by two functions and polars, and we're going to go ahead and say that we're trying to find the area inside the lemniscate, r squared equals 8 cos 2 theta, and outside the circle, r equals 2. Of course, we want to try to graph this, but before we graph it, we have to remember that if we take the square root of both sides, r is going to be equal to plus or minus root 8 cos 2 theta. And so when we put this into a graphing utility, we're going to have to use one graph for the positive root and then one graph for the negative root. And then, of course, we have r equals 2. So when we graph it, we're going to have square root of 8 cos 2 theta. Then we're going to have another one we're going to add, and we're just going to take the opposite of this. So opposite of that. Okay. And then finally, we have r equals 2. Okay, so what we're looking for is we're looking for the area that's outside of the circle, but inside the lemnicon. Okay, or I'm sorry, the lemniscate. And so what we're really looking for is just this area, and then on the other side, this area over here. So let me draw the area first, and then we can go ahead and start computing some of the bounds as well as some of the other things that we need. And so basically, that's pretty bad drawing, sorry. All right, if we look at the drawing that was constructed before, we basically have like a loop on this side. I had erase instead of draw. So we have a loop on this side, and then we have a loop on this side. All right, so it kind of looks like that. And then we have a circle, which is r equals 2. And the area that we're actually looking for, again, is inside the lemniscate, but outside the circle. Okay, so this is what we're looking for. And it would probably behoove us to just look at one of these. All right, so this is quadrant 1, and we have our circle. Okay, but then we have the lemniscate. And so if we found one of these, we notice that the other 4 are symmetric. So we can multiply whatever we get by 4. And so if we knew what this point of intersection is, okay, so in other words, where r squared equals 8 cos 2 theta and r equals 2 intersect, okay, and then we also knew what this point was, okay, so in other words, where the angle is 0. So right here, this is when theta equals 0, just to make sure. Then we can go ahead and try to figure out what the bounds are for this. Okay, so first of all, I'm going to substitute 0 back in for theta. Okay, so and I'm going to use the positive representation because we're in this first quadrant. Okay, so we know that r is positive in the first quadrant as well as the fourth. So when theta is equal to 0, and we just want to make sure that that really is the point where theta equals 0 and not the pole. Okay, so that means that we would get r squared equals 8 cos of 2 times 0. If we took the square root and we remember that the cosine of 0 is 1, that means that r would be the square root of 8. And if we go back to the graph, square root of 8 or square root of 8 is just a little bit less than square root of 9, which is 3. So it makes sense that right here would be theta equals 0. Okay, so we confirmed that's a pretty horrible looking theta equals 0, but theta equals 0 at that point. So that is going to be our lower bound for A. Now to figure out B, what we're going to do is we're just going to substitute 2 back in for r squared. So we get that 2 squared is going to be equal to 8 cos of 2 theta. Or in other words, 1/2 equals cos 2 theta by dividing both sides by 8. We know that the cosine of theta equals 1/2 when theta is equal to pi thirds, okay? Or 5 pi thirds, but we're not going to worry about that one. And so 2 theta equals pi thirds would imply that the angle is going to be theta equals pi 6 by dividing both sides by 2. All right, so now what we can do at this point is we can go ahead and set up the integral. All right, and it kind of makes sense that theta would be equal to pi 6 because the angle looks like that. Now, if we look at the actual graph, not my graph, theta certainly looks like it's a little bit better for pi 6 right here at this point of intersection. Okay, so all that being said, we're going to go ahead and set up the integral for this. Okay, so we're going to have 4, because remember, we're multiplying by 4 to get all the areas. Integral from 0 to pi 6, not pi halves, excuse me. Right. Then we have 1/2. And remember, we're going to take the outer minus the inner. Okay, so the outer is going to be the limacon. And remember, we have that r equals the square root of 8 cos 2 theta. So this is going to be the square root of 8 cos 2 theta. And we're going to square that minus the inner, which is going to be 2 square d theta. Okay, so that's going to be our setup for this. Now, simplifying this just a little bit, we know that 4.5 is going to simplify to 2. We're going to square the square root. This should be pi 6. I don't know why I really want it to be pi halves. Probably because I know it's easier to work with pi halves than pi 6, but it is what it is. And we're going to have 8 cos of 2 theta minus 4 d theta. And we don't have to use the power reducing formula this time. Okay, so that's good. So now we integrate, we get 2 times the integral of 8 over 2, because remember, we're using the reverse of the chain rule, we're dividing. This is going to be sine of 2 theta minus 4 theta d theta. We're going to substitute pi 6 back in. All right, so when we do that, we're going to end up with 2 times 4 sine of pi 6 times 2 minus 4 times pi 6, and then minus 2 times 4 sine of 2 times 0 minus 4 times 0. All right, now 4 times 0 goes away. Sine of 2 times 0 is sine of 0, which is 0. So this whole second expression is just going to go away. If we distribute through, we're going to get 8 sine of pi thirds minus, and we're going to multiply that by 2. So that's going to be 8 pi over 6, or 4 pi thirds. Okay. Last thing we have to do, evaluate a sine of pi thirds. We're going to look at the unit circle and recall that that's going to be root 3 over 2. So our final answer for this is going to be 8 times root 3 over 2 minus 4 pi thirds. Okay. Or another way to write that would be 4 roots of 3 minus 4 pi over 3. Or if we got a common denominator of 3 and then we factored out a 4, okay, another way to write this is we could write this as 4 quantity 3 roots of 3 minus pi divided by 3. Okay, and of course, if you don't trust me, you could just distribute and simplify. This is probably like the back of the book answer. This answer is perfectly fine as well. All right, as long as it's simplified down. Okay, all right. Of course, we could get an approximation of that, and we probably should get an approximation just to make sure we get a positive area, right? If we don't get a positive area, then something's wrong with us, okay, or at least with our problem. So just making sure that we get a positive area. 4 times the square root of 3. Oh, let me do that again. So I'll just multiply square root of 3 first. So 3 square root times 4. Okay, so that's like 6.93. All right, so we'll just hold on to that. And then 4 pi over 3. So we would have 4 pi over pi went divided by 3 is 4.19. So we know that it's going to be positive. Okay, so that's good because remember we had 6 something minus 4 something. All right, so that's just a check just to make sure that at least you're not getting a negative area. Okay, All right, so we have one more of these that we'll look through with respect to areas, and then we're going to move on to arc lengths.